Okay, let's talk about microcontrollers finally. A microcontroller is this really cool, exciting piece of technology that's like a tiny little computer all on a little chip, or in the case of the one that we use, an Arduino, on a carrier board that allows you to really easily interface sensors, motors, buttons, lights, whatever you can think of to it in a quick and easy way for prototyping. We're going to look at microcontrollers or introduce them sort of at a really broad scale at the start, just because they're very, very different than what most people are used to. If you're coming at this from computer science or coming at it from sort of any sort of computing sense, most of the code that you've written, if you've written it in Python or whatnot, has been executed on a desktop computer that's just very, very different kind of thing than a microcontroller. Before we get into that, microcontroller looks something like this, or this is an Arduino in particular. And the Arduino is the name for the board, which is sort of a prototyping platform that allows you to sort of quickly and easily attach things to it, as I was saying before. The chip itself, the microcontroller itself, is the chip. In this particular case, the particular chip on here is called an Atmel328, but there are literally thousands of different kinds of microcontrollers, and they vary in a lot of different ways, like how many pins they have on them so that you can control more things, the kinds of communications protocols that they have built into them, how much RAM or ROM they have built into them, what other kind of peripherals like analog to digital converters that they have in them, whether they're fast, whether they're high power or low power, whether they're cheap, and so on and so forth. And so just sort of to quickly orient you to the board, the chip here itself is the microcontroller. Everything else on this board is just basically to make our lives easy when we want to use and talk to the microcontroller. And so this is a USB port for talking to or communicating or programming largely the microcontroller, and it also has a serial console that we can use to communicate back and forth. There's a little teeny tiny chip there. That's basically a USB to serial bridge that allows us to go from the protocol that the USB port uses into something called a UART, which is a protocol that most microcontrollers speak. There's a bunch of other smaller stuff on here that isn't too exciting for our senses. Here's a crystal that runs the main clock of the microcontroller. Here's a bunch of power capacitors for an external power input that allows us to use up to, I think, 9 volts on these boards and bump it back down to something that the microcontroller uses. Most microcontrollers operate at either 5 volts or, much more commonly, 3.3 volts. Though a lot of the ones that are good for sort of easy prototyping stuff like the Arduino here, a lot of these operate at 5 volts. This little part here is called a linear regulator. It's a voltage regulator that takes whatever happens to go in here up to a certain voltage, probably a upper range of 9 volts, and bumps it back down to 5 volts to power the microcontroller itself. And then these sort of rows of pins here are meant for you to either connect different wires to or connect different circuit boards to directly on top of it and whatnot. And that's basically the broad strokes. Everything else is either some resistors or capacitors or other sort of glue logic to just sort of get the thing up and running and for us to play with it. And it also has this handy dandy reset button so that if your program freezes or for whatever reason you need to reset it to the start of the program, that's where it is right there. So let's talk about the difference between a microcontroller and a CPU because they're quite a bit different. And so the CPU would be something like you have in your desktop or your laptop, and basically the thing that most of you will probably have done nearly all of your programming for so far. And so for a CPU, or for a desktop computer, nearly all of the RAM or ROM or the hard drive capacity or whatnot that you have, it's all external to the CPU, external to the chip itself. In general, it's a little bit of an oversimplification. There's a cache in a CPU that keeps a little bit of very fast RAM, But in general, most of this is external. I'll just write ext here. And it's big, right? It's usually sort of on the scale of gigabytes. Now for a microcontroller, it's all internal, usually. And you generally might have RAM in the range of anywhere from 2 kilobytes to 64 kilobytes. That's obviously not huge. And you might have ROM, or flash storage, or the thing that you keep your program in, that's anywhere in the range of 32 to 128, sometimes a little bit larger, kilobytes. So it's very, very much less, right? Can you imagine, as you soon won't have to imagine, because you'll be doing it, writing a program that only has 2K of memory total for the entire execution. And so if you make an array that has 1,000 elements in it, and those 1,000 elements use 2 bytes each, say for an integer, low resolution integer by desktop standards, you've used your entire program memory, you can store nothing more, and your program will just go tilt. So it's much, much less program space, and it really forces you to think very differently about efficiency. In terms of I/O, or input and output, CPUs generally don't consider a lot of this. There's generally very minimal I/O ports for driving external components like lights and motors and things like that. Whereas microcontrollers generally have quite a bit of this, and that's basically their niche, is that they're basically usually used as something that interfaces with real stuff in the real world, motors, lights, buttons, things like that. And in fact, you can have systems that have both CPUs and microcontrollers, and the microcontroller acts as sort of the middle person between the real world stuff you're trying to control and the CPU. In terms of speed, you know, the desktops that we tend to sit in front of these days are somewhere on the order of 2 gigahertz. Microcontrollers are not anywhere near that fast. And the ones that we use commonly are generally anywhere between 8 and 16 megahertz. And so that's obviously several orders of magnitude slower than most of what you're probably used to. Though remember, that's still 8 million instructions per second, which is very, very fast, especially when you don't have an operating system to consider, which is something that I should also mention. So all of the code that you've been writing so far has probably been on an operating system, or a system with an operating system. So you have lots sort of given to you by, you know, Linux or Windows or Mac OS or whatnot, but there is absolutely nothing for a microcontroller. You're writing on the bare metal. The CPU is executing your code and only your code. There's no kernel, there's no memory manager, there's no nothing. It's just the bare metal. So that means it's very fast, but it also means that coding for it can be a little bit more complicated. In terms of current, so the amount of current that the devices use, modern CPUs use quite a bit of current. And if you've ever seen the heatsink on a modern CPU, they're very, very large. They have to dissipate quite a bit of current, whereas microcontrollers tend to be very low current, and because microcontrollers are often embedded in devices that are battery powered, there's a huge market for microcontrollers that use as little current as possible. So some of them are even down into the microamps or even nanoamps, I think I've seen, for sleeping. So they can last for years on a battery just by sipping it and going to sleep and waking up and periodically and doing whatever they need to do, and then going into a lower power situation. Now, in terms of cost, there's also a big divide between CPUs and GPUs. You're probably going to have a hard time finding a CPU that's any less than $100, and they tend to be sort of in the $100 to $1,000 range. That's very, very different than microcontrollers, which are meant to be very inexpensive since they're just in devices. And so these tend to be anywhere between a dime and all the way up to maybe $10 for the most expensive microcontroller you're likely to find. That's wildly different, right? And most of them are in about the $1 to $2 range that you're likely to encounter and have in a product. And you can think that if you're designing a product and you put a microcontroller into it, if you're going to build 1 million of them, if you save $1 on a microcontroller because you've been able to reduce your design down to something that will run on a very cheap, very inexpensive microcontroller, then suddenly you've saved $1 million. So that's why we usually design for the lowest common denominator. In terms of peripherals, and what do I mean by peripherals? I mean things that we haven't really encountered yet, but things like the ability for the device to do analog to digital conversion, so it can measure analog voltages, which, if you remember talking about resistor dividers, that gives us the ability to potentially interface with different kinds of sensors. Or the ability to have SPI or I2C, which are special multi-wire communication protocols that are usually used for low-level sensor interfaces. In terms of that, peripherals, CPUs tend to have some, especially these days. Historically, they've had almost nothing. But microcontrollers tend to have lots. They tend to be feature-rich. And so if you're looking for microcontrollers in the higher price range, they tend to have more peripherals built into them, essentially. That makes your life a little bit easier and makes communicating with different kinds of things a lot easier. And then in terms of math, so by that I mean arithmetic, usually CPUs are heavily optimized and have a lot of silicon devoted just to doing mathematics very, very fast. This is usually called the ALU, or arithmetic logic unit. A lot of CPUs these days don't just do single cycle multiplication, but they do, single cycle many multiplications. And so if you're running at 2 gigahertz or 2 billion hertz per second or cycles per second, you can do, around 2 billion multiplications per second, which is just fantastic. That's a different story over here. Microcontrollers tend to have a minimal arithmetic logic unit. Usually you get addition and subtraction, but not multiplication or division unless you've really forked out for a higher cost microcontroller. And so that means that doing math can be incredibly slow on these things, especially if you're doing division, because they have to simulate that in software. You usually don't have to simulate that in software unless you're coding in assembler, but for the coding that we're going to do in a high-level C language, the compiler usually has to handle that for you. And so if it sees a division or a multiplication, it generates the code in assembly to do that for you. If you're talking about floating point, so numbers with decimals in them, basically, or real valued numbers, doing floating point arithmetic is extremely expensive on microcontrollers because it's all simulated in software. And so adding and multiplying and dividing in real valued numbers is very, very slow. So this is largely the difference. And you can see sort of here that they occupy very different sectors. So for a CPU, you'd mostly want to use this for computing, and most of the things that you do use a computer for day to day. Whereas for a microcontroller, these are really about interfacing to the world and making physical devices that don't really need a lot of computational power, but that are focused on mostly just interfacing and interacting with the world.